Hi and welcome to this Leaving Certificate Applied Maths video where we're looking at Hooke's Law. In this video, we're going to look at an introduction to Hooke's Law. We're going to explore how force and displacement are linked when we're looking at elastic materials. We're going to solve some problems involving springs and elastic strings. We're going to connect Hooke's Law to horizontal circular motion, so looking at conical pendulums where an elastic string is used. And then we're going to connect Hooke's law to differential equations. So this is higher level only. And we're going to explore the idea of work done and elastic potential energy. So this video is suitable for all applied math students. We're going to start with an introduction to Hooke's law. Then we're going to start easy examples before moving into more challenging higher level questions from the mock papers and then into differential equations. Feel free to skip through to a section of the video that best suits you. So on the screen, I have a screenshot from PhET simulation, which allows us to understand how different masses affect the spring in different ways. So I have two springs here, and they are both the same strength. And we can see that the 100-gram mass pulls the spring down further than the 50-gram mass. Now, looking at that, you may not straight away notice a relationship. However, if we put in some lines here, so the blue line shows me what the spring length would be if there was no mass hanging on it. The red line, I've just added in an extra line just to show us where the 50-gram mass has extended the spring to, and then the green line shows us where the 100-gram mass has extended the spring to. So what we can see here is there is a relationship between the extension, not the actual length of the spring itself, but how far it's extended beyond its what we call natural length. So what that's shown here with that blue line, that unstretched length. So it's really important when we're working with Hooke's law that we understand it is all about that extension. I put the link to this PhET simulation in the description below. It's really nice to play with if you haven't got an actual spring balance. So on page 57 of our log tables, we get a formula for Hooke's law. So it is given as F equals minus Ks. Now this F is our force. This is the force due to Hooke's law, or it is a restoring force. K stands for the elastic constant. This will be something you're either given or have to work out. It's different for every spring and every string. And then S is our displacement. So that is the distance that the spring has been stretched. Now that is not its actual length. It is the change in length. And that's really, really important. So Hooke's law states that within a material's elastic limit, because there is a limit, the amount it stretches is directly proportional to the force applied. Now, this idea of directly proportional is something that we meet every now and then. It's a really important idea. So this is a great chance for us to explore it. So we're told that the force is proportional to the amount that it stretches. So I've just put my modulus signs or my absolute value signs there on the right hand side, which I'm just currently saying that the force is proportional to displacement, but I'm not talking about the direction for just for a minute. So this symbol here in the middle, that means proportional. And how we can remove that symbol when it's directly proportional is by putting in a constant as the coefficient. So by putting in a multiplier. So if F is proportional to the absolute value of S, we can say that F is equal to some constant times this absolute value of S. So in this case, we're saying it is called the elastic constant Ks. So this is a great way when we're working with anything proportional that we change that idea of proportional into an equation, and something we see a lot with differential equations. So then if we think about the actual direction of this, we're going to think of it as a negative. Now what that minus really means, it is a restoring force. So it's working against where it's being moved to. So if you think in terms of your string or a spring, you will pull the spring, and the force is trying to pull it back. It's restoring it to its natural position. We're talking about it working in the opposite direction to the stretch. So that minus is all about the direction. Now, the reason I'm making quite a big deal about this is often in a question when we're working with Hooke's law, we're drawing our force diagrams, and in that we have our arrows showing direction. So often we ignore that minus. We simply focus on the magnitude of the force, so the size of the force, rather than putting in that minus. We deal with the direction separately. So in the definition for Hooke's law, we have this idea of directly proportional. Now, this is something that's highlighted quite a bit on the junior cycle course, but if it's something you haven't seen in a while or you're not sure what it means, we're basically just talking about where two quantities increase or decrease at the same rate. So they are directly proportional. So if one quantity doubles, then the other also doubles. So if one halves, the other halves. What's really key about this is if we graph it, and I'm going to show you some graphs in a second, the graph is going to be a straight line, but it's going to pass through 0, 0. It's going to pass through the origin, which if we think about this in terms of our equation of the line, it's going to be a y equals mx. There is no constant, or the constant is 0. So here are three graphs, and we're wondering like, well, which ones show directly proportional? So A does, B does, C does not. It is linear, but we could see here that this will be in the form y equals mx plus a constant, and the constant represents the y-intercept. Here it's just under 2. So these would not be directly proportional. So if you think about maybe some conversions we would have that would be directly proportional versus some conversions that are not, the easiest way to identify them is think about when the number is 0. So for example, if you are cooking or baking, you could be using grams, kilograms, or you might be using pounds and ounces. So 0 pounds is equal to 0 kg. So that is something that's going to be directly proportional. However, if we think about temperature, so degrees Celsius and degrees Fahrenheit, 0 degrees Celsius is not equal to 0 degrees Fahrenheit. So that means they are not directly proportional. There is, of course, a relationship and a linear relationship, but it is not direct proportion. So just revisiting our formula here from our log tables, I just want to talk about the fact that we probably won't be using it in this form for our basic questions. So let's look at, I suppose, the information we'll be given in a question and how we can change this formula slightly to be a bit more useful. So in a question, we're going to be working with our force, our elastic constant, and our distance of or displacement of the spring stretch. However, we will be talking about two other measurements, and that is L0, which is our natural length, and L, which is our extended length. So rarely are we given this displacement, that S, how far the spring or string has been stretched. More than likely, we're going to have to calculate it. So if we were thinking in terms of the natural and extended length, the formula becomes F equals minus K L minus L0, which is the extended length minus the natural length. Now, just to kind of really see that, here's an example. So I have on the left a spring, and it is 5 centimeters long. It is then going to be extended because I'm hanging an 80-gram mass off it. Okay, so an 80-gram mass has been hung off this spring, which is going to then stretch it so that it is now 8 centimeters. So my natural length is 5 centimeters, and my actual extended length is going to be 8 centimeters. We just need to be very careful here. We're working always with our SI units, so we're going to convert those into meters. And then we can think about that displacement, which is the difference between them. So that extension. So how far has the spring been extended? And the answer is going to be either 3 centimeters or 0.03 meters. So this is more than likely how we're going to be approaching questions. It's rare that we're just given or looking for that extension. So let's jump into an example. So a spring has a natural length of 15 centimeters. When a block of mass of 500 grams is hung from the spring, its length increases to 17.5 centimeters. Calculate the elastic constant of the spring. So let's see what we have. We have our spring. As soon as we hang the mass on it, it is going to extend. So our natural length of our spring is L0. And this question that tells us that that's 15. And then we have an extension when the mass is hung, and that's 17.5 centimeters. So a few things that you need to be careful with. The first is make sure you're working in SI units. So this is 0.15 meters. Here is 0.175 meters. This is 500 grams, but that is going to be 0.5 kg. Kg is our SI unit for mass. So we need to work out now our elastic constant. So when we're working with our force, we need to go back to our basics on forces. So when this 500-gram mass is hung, the system is now in equilibrium. It's not moving, which means my weight, which is mass times gravity, which is 0.5 by 9.8, which is 4.9 newtons, is going to be balanced with this restorative force F. So this must also equal 4.9 newtons because we're in equilibrium. And how we know we're in equilibrium is because they've told us that the length increases to 17.5. That is telling us that this is not bouncing, it's not moving, it is solid. The forces that are working up are equal to the forces working down. So then filling into our formula for Hooke's law, we have our force, which we know is 4.9, is equal to, again, I know that my force is moving up. I don't need to put that minus in here. I can simply just use the magnitude of this force. So we're going to just ignore that minus. Another way you could think about is that the force working up is negative. Put a negative on both sides. Both are absolutely fine. L then is my extended length, 0.175, minus my natural length, 0.15. That gives me 4.9. K, 0.025. K is equal to 4.9 divided by 0.025. And we get 196. So what are the units for K? Well, think about what our units are here. 4.9 was a force, so that's in newtons, all over our length, which was measured in meters. So our unit for our elastic constant is Newton per meter, which you can write as Newton/m or Nm to the power of -1. Example 2. A spring has a length of 22 centimeters when a 2 Newton weight hangs from it. The spring constant is 50 newtons per meter. Calculate the natural length of the spring. So again, let's draw this out. We have a spring. It then gets a 2 Newton weight hanging off it. Bear in mind here we're given the actual weight, not the mass. We have L0, which is what we're looking for, and we're given the length. So this here is 22 centimeters, which is 0.22 meters. Our mass is 2 newtons. So again, we know that we're working in equilibrium, which means that our forces up and forces down must be equal. Everything is balanced. So we have our weight acting down. our weight is given to us just as 2 newtons. We then have this restorative force working up. Because we're in equilibrium, this is also going to be 2 newtons. Filling into our formula for Hooke's law, that tells us that the force is going to be equal to K, which we're given in this case. It's our 50 newtons per meter, times L, 0.22, minus our natural length L0. Now, if you prefer, you can call that X, you can call that whatever you want. So let's work that through. I'm going to divide both sides by 50 rather than multiplying it in, but you're welcome to work this whatever way you like to solve it. So we get L0 is equal to 0.22 minus 2 over 50, and then we can go to our calculator and get our final answer of 0.18 meters or 18 centimeters. Example 3. A spring has an elastic constant of 12 Newton per meter and a length of 25 centimeters. An object of mass 20 grams is attached to the spring. What is the new length of the spring? So here we have our spring before anything is added onto it, and then here we can see it extended with that 20 gram mass. Be really careful. 20 grams is not in our SI unit. We need to convert that to kg, so that's 0.02 kg. So we have our natural length here, and that's 25 centimeters or 0.25 meters, and we're looking for our length L. Okay, so that's the extended length. So here we have our formula, F equals Ks, but then we're looking at L minus L0 instead of our displacement. Again, we're ignoring the minus because we're thinking in terms of magnitude. The direction is already taken care of in our diagram that we're about to do. So we have our weight, which is mass times gravity, which is mass 0.02 times gravity, which is 9.8. And that gives us 0.196 newtons. We then have our restorative force, which is working upwards. That's where that negative is coming in. It's telling us the direction. Because this is in equilibrium, we know that the forces up must equal our forces down, meaning that restorative force is equal to 0.196. So 0.196 is equal to K, which we're told is 12, our extended length, which we don't know, minus our natural length, which is 0.25. So I'm going to divide both sides by 12. You are welcome to multiply it out. This is just a little bit quicker. And then when I get my 196 divided by 12 and I add my 0.25, and now I can just go to my calculator once rather than doing a few different calculations. So we end up with 799 over 3,000, and in a decimal 0.266 meters, which is 26.6 centimeters, since we were given the centimeters originally in the question. So let's take a look at example 4. We're just making it a little bit more challenging. So this is going to follow the same logic of Hooke's law, but we're told that the particle is positioned on a smooth horizontal table between two walls. The walls are 15 meters apart, and then on the left-hand side, the particle is connected to a spring of natural length 0.8 meters, elastic constant 4 newtons per meter, and on the right-hand side, it's connected by a spring of natural length 1.5 and elastic constant 2 Newton per meter. So we're looking horizontally rather than vertically now. So here are my two walls and the table. They are 15 meters apart, and we have a particle somewhere. And the question we're being asked is to determine the position of equilibrium. So remember, equilibrium means that everything is balanced. So in this case, our forces to the right are going to equal our forces to the left. So we don't know exactly where that position is. That's what we're being asked to figure out. So we're going to have to label one of these sides as the unknown You can use any letter you want. L because it's the extended length. I'm going to use X because it can often just be a little bit easier in algebra questions to have X. L can be easily confused for a 1. I tend to do a loopy L, but let's keep it for X for the moment. So it doesn't matter which side we work on. I'm going to work on the left, so I'm going to call that X. I don't want to bring in another variable or another unknown, so I want to try and write that right-hand side in terms of X. So remember, I know that that full distance is 15, which means actually that right-hand side can be written as 15 minus X. I'm now going to fill in all the other information that I have on this diagram. A diagram is always really, really helpful to visualize what's going on. So we have a natural length of 0.8 meters and a K, which is our elastic constant of 4 Newton per meter. On the right-hand side, we have a natural length of 1.5 meters and a K that is 2 Newtons per meter. So if we want to think in terms of our forces, we now have our particle with the force pulling it to the right. This is our restorative force or force due to Hooke's law, and then we also have one going to the left. Okay, so the ball is being pulled in both directions in such a way that they are balanced. The direction here is because the spring is trying to get back to the wall that it's attached to. So the spring on the right is pulling the particle to the right. The spring on the left is pulling the spring to the left. So what we're going to do is create these force equations for each of them. So I'll go the left-hand side, FL. So our K, remember we're ignoring the minus because we've dealt with the direction by showing the arrow to the left. We then have L, which we don't know. We've called it X, minus our natural length, which is 0.8. Our force to the right is going to be K. Again, we're just talking about the magnitude of this force. And then we have 15 minus X, which is our L, minus 1.5. We are basically saying the forces to the left are equal to the forces to the right. That is what equilibrium means. So we get 4 times X minus 0.8 is equal to 2 times, I'm going to clean this up slightly, so I have 15 minus 1.5, which gives me 13.5 minus X, so I get 4X minus 3.2 is equal to 27 minus 2X. This gives me 6X equals 30.2, and then we divide both sides by our 6 and we get 5.03 meters, and that's just rounded to 2 decimal place. Now it said determine the position of equilibrium. Now that's not enough. Now I know we've shown our X on the diagram, but we need to be very clear what this means. So the position is 5.03 meters from the left-hand wall. Because if we had set this question up differently, if we had put the X on the right hand side, we would have got a different value for X, but it would have been comparatively the same. It would have been looking at the right hand side rather than the left hand side. So just make sure with the position that you're giving enough information. So part 2 of this question asks us to find a position where there is a resultant force of magnitude 10 newtons acting on the particle to the right. So what that means is rather than being in equilibrium, we now have a resultant force. We have the right force 10 newtons bigger than the left force. So what this simplifies to is the forces to the right take away the forces to the left will result in 10 newtons. So other than that, our process is going to be pretty much the same. We don't know the length, so I'm keeping the X as my unknown. And we're going to work through it in the same way. If you want, we can use our equations that we made in part 1. I don't have them on the screen, so I'm going to just put them down again. 4 times X minus 0.8 here. Forces to the right. 2 times 15 minus X minus 1.5. We are saying that forces to the right are bigger, so take away the forces to the left and we're going to be left with 10 newtons. So that is 2 times, I'm just doing a little bit of cleanup as well as we go, minus 4 times x minus 0.8, and that equals 10. 27 minus 2x minus 4x plus 3.2 is equal to 10, minus 6x plus 30.2 is equal to 10. So 6x is equal to 20.2. So x is going to be 20.2 divided by 6, and that gives us 3.37 meters rounded to 2 decimal places. It comes up 3.36 recurring, 666, so that's 3.37. So what we need, again, we're talking about its position, 3.37 meters from the left. Example 5. So this example links very strongly to circular motion. We're looking at a conical pendulum. The difference between this question and the ones we've seen in horizontal circular motion is that we're looking at an elastic string here versus an inelastic when we're in circular motion. But the process is pretty much the same. We're just going to introduce the element of Hooke's law into this question. So if you haven't already revised it, or if you're not familiar with conical pendulum questions, I suggest you look at those. I will link the introduction to horizontal circular motion video in the description below. Just skip to the conical pendulum example before you look at this one. So we're told that the conical pendulum consists of a particle of mass 2 kg attached to an elastic string with elastic constant 49 Newton per meter. The string is fixed to a point Q and the particle moves in a horizontal circle of radius 0.9 meters with the center of the circle 1.2 meters vertically below Q. So here, the first thing we're asked to do is to find the length of the string when the particle is in motion. So here we work through a little bit of Pythagoras. Hypotenuse squared is 1.2 squared plus 0.9 squared. So C is 1.5 meters. So then it asks us to calculate the elastic force acting on the string. So we have weight, which is acting down, which is mass times gravity, which is 2 times 9.8, which is 19.6 newtons. We then have a restorative force. So this force here is that force due to Hooke's law. Our acceleration is towards the center of the circle, so everything we want, all the forces, we want them resolved horizontal and vertical. So resolving that horizontal force, the first thing we realize is actually we don't actually have an angle. So let's place an angle here, and that way we can get a sine and cos from this triangle. So sine is opposite over hypotenuse, so 0.9 over 1.5, and that simplifies to 3 over 5. Cos is adjacent over hypotenuse, 1.2 over 1.5, which simplifies to 4 over 5. So then if we're working to resolve our force, we have part of it going vertical and part of it going horizontal. Our angle alpha is there, and it can also be placed here. That is the ideal of alternate. So here we have S sine alpha. Here we have F cos alpha, and our weight is 19.6 newtons. So just giving ourselves a bit more space, I can change this to 3f over 5 because sine is 3 over 5 and 4f over 5. Then we work with our normal steps with horizontal circular motion, which are forces up equals forces down. So our forces up are going to be 4f over 5 equals 19.6. So we can work out F as 19.6 multiplied by 5, and then divided by 4, which gives us 24.5 newtons. And that is my restorative force. That is the elastic force acting on the string. Then what we're asked to do is to find the natural length. So our natural length is going to be using Hooke's law, which is F is equal to minus Ks. For us, we're going to use the version of KL minus L0. Our force is 24.5. Our K is 49. Our length is 1.5 minus L0. L0 is then going to be, we want to do 24.5 divided by 49, and then we make that negative and add 1.5, and we work that through, and it works out as a length of 1. Then we're thinking in terms of our centripetal force. That's going to help us get our angular velocity. Remember, we have two questions. What force is acting as centripetal force? And this is the horizontal component of that restorative force. And then which formula should we use and why? Well, they asked us for angular velocity, so we're going to work with this one here. So our centripetal force is going to be 3F over 5 is equal to m or omega squared. That is 3 times 24.5 over 5 is equal to 2 times our radius, omega squared. So omega is going to be the square root of 3 times 24.5 all over 5 by 2 by 0.9. That gives us 2.86 radians per second. Now I've done that in one go just to save me time on the calculator, but you're welcome to break that into piece by piece. This is question 10 part A from the 2024 ordinary level exam craft paper. A particle of mass 3 kg is attached to the end of an elastic string of natural length 1.5 meters and elastic constant K Newton per meter. The other end of the string is fixed to the ceiling. The string extends to 2 meters in length when the particle is attached. Find K, the elastic constant of the string. So here's our scenario. So our formula is F equals minus Ks. We're going to ignore the sign because we're focusing just on the magnitude, and instead of our displacement, we're going to use L minus L0. So our K is what we're looking for. Our length is 2 meters. Our natural length is 1.5 meter, and we need to figure out our force. So when the 3 kg is hung, we get weight, which is mass times gravity, which is 29.4 newtons, and that means that our restorative force F will be equal to our weight because it is in equilibrium. So we get F is equal to 29.4 newtons. So we get 29.4 is equal to K times 2 minus 1.5. K then is equal to 29.4 divided by 0.5, and we get 58.8 newtons per meter. This is question 1 part A from the 2023 higher level exam craft paper. A particle of mass 5 kg hangs at the end of an elastic string of natural length 1 meter and elastic constant K Newton per meter. When the string is extended, this string is 2.4 meters in length. Find the value of K. So our formula is F equals minus Ks. We're going to ignore the negative because we're going to take account for the direction ourselves, and then we change our displacement to L minus L0. So in this case, our K is unknown. We want to work that out. Our length is 2.4. Our L0 is 1, and we need to figure out our force. Because the system is in equilibrium, our weight, which is mass times gravity, which is 5 times 9.8, so 49 newtons, is equal to the restorative force, which is pulling it back up. So that is also 49 newtons. So we end up with 49 is equal to K, and then 2.4 minus 1. So K is equal to 49 divided by 1.4, and that gives us 35 newtons per meter. Part 2 of the question then says find the length of the string if a particle of mass 8 kg was used instead of the 5 kg. So in this situation here, we're going to have our 8 kg, which is going to be heavier. So 8 by 9.8. Now, what that means is we're still in equilibrium. Our force still has to match it. Obviously, the restorative force in this case is stronger, it's bigger than the force in the part 1. However, to account for that, so if we look at our formula, to account for this, what's going to have to happen is K is going to stay the same. Sorry, that's going to stay the same. And force has gone up, meaning S is also going to have to go up. So the displacement has to go up to match the force. K is going to stay constant. So that formula, we're going to use a version of it. We're going to ignore our negative because we're taking our direction into account ourselves on the diagram. So K is equal to L minus L0. So our force, 78.4, is equal to K times. In this question, the natural length is still the same. That hasn't changed. But what I don't, or sorry, this we do know our K, that's 35 because that hasn't changed. Our natural length hasn't changed, but we don't know our L. So we have L minus 1. So L minus 1 is equal to 78.4 divided by 35. And then to work out L, it's going to be 78.4 divided by 35 and then add our 1. So 78.4 divided by 35 gives us 2.24 plus 1, which is 3.24 meters. This is question 9, part B from the 2024 higher level exam craft paper. An engineer is trying to model a new activity for children at a fun fair. In the model, it is assumed that a child is on a seat which is suspended from a horizontal surface PQ by 2 elastic strings, as shown in the diagram. It is assumed that the mass of the participant and seat is 90 kg and the system is in equilibrium. The strings make an angle of 60 degrees with the surface PQ and both have an elastic constant of 221.4 Newton per meter. And have a natural length of 120 centimeters. Okay, so there's quite a lot going on in this question, but luckily we were given a lovely diagram. So L0 is equal to 1.2 meters. We have our value of K here, and we're being asked to calculate the extension. So the first thing we're going to do is we're going to explore the idea of the forces. And remember, they told us that the system was in equilibrium. So the first thing we have is our weight. Weight is mass times gravity. They've told us to assume the weight is 90. So that's 90 by 9.8, which gives us 882 newtons. And that, 882 newtons. And that is balanced by 2 restorative forces. We have a force going this way, which I'll call F1, and a force going this way, which I will call force 2. Now, these need to be resolved because we want to talk about forces matching or balancing. So we want these resolved perpendicular and parallel to our weight. So we want to have them vertical and horizontal. So let's do a bit of resolving on our first diagram and we'll go from there. So this force 1, let's start with force 1. I can break that into a horizontal component and a vertical component. Let me move the vertical component over a little bit. So we end up with 2 pieces here. And the bit that I suppose is the most important for us is to understand, well, where is the angle? So if my 60 degrees is here, it's also here because they are alternate, meaning I get this F1 So the vertical one is the opposite side, so that is sine 60. Our horizontal is adjacent, so this is F1 cos 60. I can do something very similar over with my force 2. So there are my two components. 60 degrees is here, so this is F2 sine 60 because it's the opposite side, and this is F2 cos 60, which effectively means that these forces are not needed anymore. So we have instead F1 sine 60, F1 cos 60, F2 sine 60, F2 cos 60. So I'm going to show these all on a diagram just a little bit cleaner so we can make sense of it. So we have our weight, which is mg, which is 882 newtons. We then have F1 cos 60 to the left, F1 sine 60 coming up. We have F2 cos 60 to the right and F2 sine 60 coming up. We can sub in for our 60 degrees and do some calculations. But first, I'm going to think in terms of my equilibrium. Let me just move this out of the way. So equilibrium means forces to the right are equal to forces to the left, and forces up equal forces down. Now, if I look at forces to the right equal forces to the left, or to the left equals forces to the right, whichever we want to think about it, we get F1 cos 60 is equal to F2 cos 60. They both have a cos 60, which I can get rid of those. So basically what we're saying are the two forces have to be equal. Force 1 and force 2 have to be equal. The two restorative forces are going to be the same. Now, maybe that was instinctual. Maybe you kind of already knew that, and that's fine, but this proves it. So what we're going to do then to make life a little bit easier is we're going to say that F1 equals F2, and we're just going to call it F. So let's say F1 is the same as F2. So let's just, for simplifying everything, call it F. So I'm going to call these F sine and F cos. Makes life a little bit easier. We've already said that the forces to the left equals forces to the right. And now we can see they're identical, so that's absolutely no help to us. So what we're going to look at now with our equilibrium, our forces up must equal forces down. So we get F sine 60 plus F sine 60 is equal to 882, which is basically 2F sine 60s. Now we can plug in for sine 60, sine of 60, root 3 over 2. So then we have a 2 in front and a 2 underneath, which gives us root 3F is equal to 882. So our force, our restorative force, is 882 over root 3 newtons, and we feel this is great. However, we need to think, well, what was the actual question? So pulling in the rest of that question, just the end of it, they told us that they both have an elastic constant of 221.4 Newton per meter, and that's our value of K. And then here they gave us our L0, which was 1.2 meters, and they asked us to calculate the extension in the strings. Okay. So we're going to use our little formulas here. So our force for Hooke's law, F is equal to minus Ks, but we're going to look at instead K times L minus L0, and we're going to take it as positive because we're already dealing with the direction. That minus is just a directional piece. So using that formula, our force is equal to K, so 221.4 times L, which I don't know, I'm just going to call it X, minus 1.2. But because we've already worked out what F is, I can now sub that in, or let these equal, whichever way you prefer to think about it. And we can basically say that 221.4 are K times X, the length we don't know, minus 1.2, our natural length, should give me 882 over root 3. Working that through, I get X equals 3.5. And then if I know my natural length is L0, that means I can figure out that my extension is 2.3. So they asked for the extension in the strings. So they're extended by 2.3 meters. Now, we didn't need to work out that extended length, okay? We didn't need that. What we could do instead was simply, in this case, leave this as S, because that's what they're asking for. The extension is the displacement. So if I change that to S, we would have had our answer here, and it would have given us the 2.3, and we would have saved ourselves like 2 extra steps. But we're quite used to working with the actual lengths, and if this had instead asked for the extended length of the string, or the length of the strings, or the current length of the strings, we would need that 3.5. But the extension, we can simply use our S. So part 2 of this question says, in a second iteration of the model, the engineer decides that he wants to double the elastic constant of the strings. What effect will this have on the tension? Now, I'm not mad about the use of the word tension when we're working with questions like this. I like to think of it more as that restorative force. So tension for me is where they're inextensible strings, where there can be, I suppose, like a tension as such, while with the elastic strings, I don't think tension truly explains it. However, we do see that word used throughout papers, throughout books, so it's absolutely fine to think about. I've called that force, not tension, the whole way through this video, but I've called that the restorative force. So what effect is, I suppose, that doubling of the elastic constant, what effect is that going to have on tension, or that restorative force? And actually, it has absolutely no effect on it, which may feel slightly counterintuitive. But think about the questions we've seen throughout this video. The force, that restorative force, is changed when the mass is changed. So it's very, very much based off the mass that's hung and the weight of that object. So mass times gravity, because that's what it will be in equilibrium with. So if there's a bigger weight pulling it down, that means it will need a bigger force pulling it up. But if all they do is change the elastic constant, then because the 90 kg isn't changing, we're not going to see any effect on the actual force itself. What we are going to see, now they didn't ask this, but what we are going to see is that the extension in the string is going to decrease to balance out the elastic constant. So look at our formula. So F, we're saying, is staying the same. We have a K that has been doubled, so that's going up. And in order for the left-hand side to stay the same, if one part goes up, something else is going to go down. Now, L0 is our natural length. That can't change, okay? Our natural length is our natural length. So the actual length there, the L, is going to come down to balance that out. So I'm going to connect Hooke's law to a little bit of differential equations. Now, this has been covered in the differential equation videos, and I've linked the differential equations playlist below. But in this video, we're just going to go a little bit deeper into kind of the thinking behind it. Bear in mind that this is a higher level only topic, and if you haven't already covered differential equations, this may be useful to see, but it may not make full sense right now. So what we're really doing is connecting our force with our energy. So when a spring stretches or compresses, it exerts a restoring force proportional to its displacement from the equilibrium. And we know that that is our definition of Hooke's law, and that's what we've been using throughout this video. So we get this F is equal to minus K. And in this section, I'm going to use the letter X for displacement. Now, if you haven't seen differential equations yet, this might feel a bit weird, but the reason we tend to use X is when we're working in calculus, X can be a little easier to work with when we're differentiating. So we do it with respect to X dx rather than ds. So let's define what all these are. So F is our restoring force, K is our spring constant, which is like a measure of that stiffness of the spring, and X is the displacement from the spring's natural length. So as the string stretches or compresses, work is done to store energy in the spring as elastic potential energy. So generally we focus on two types of energies in applied maths, and that is kinetic and potential energy. Now, one thing maybe we don't stress enough is that idea of our potential is gravitational potential energy. It's your potential energy due to gravity or its position and what gravity can do. So our formula for that is mgh. What we're talking about here is the potential energy due to the fact there's elasticity because we have a force, a restorative force. So if you can imagine, if you pull something on an elastic band or even just pull the elastic band, there is energy there that when you release it, that potential, which is an elastic potential energy, converts into a kinetic energy, into a moving energy. Now, we don't see this a huge amount, but it is something that when we get into differential equations and we can calculate or find a formula or derive a formula for this work done, we can start seeing it brought into questions. So we think of this as work done by a variable force. So the total work done by a string is calculated using this formula here, and that is from our log table. So work is equal to the integral of f dx. So that is your force integrated with respect to x, where x is your displacement. We can see that as ds if you want to use s for displacement. So here, our magnitude of F, now I'm talking about the magnitude of the force, is due to Hooke's law, because that's again where we're at in this video, and that is equal to Ks. So plugging that in, we get the integral of Kx with respect to x dx. So you can integrate that, which will get us an expression for work. And it's very straightforward to integrate. It is polynomial. So you're adding 1 to your power and then dividing by your power. So that ends up as kx squared over 2 plus some constant. Now, the integral is going to describe how the force changes with displacement and how it accumulates the energy in the spring. But what I want you to remember here, and this is very simplistic, but work is scalar. So that's why we're using the magnitude of force here. Work is a scalar measure. So work doesn't have a direction. When we talk about work done, we are literally saying this is scalar. Remember, your energy is scalar as well. So when we're plugging in our force, we're going to plug in our force as a magnitude. Now, it's a little bit overly simplistic, but if you're happy with that, stop listening. If you're kind of like, okay, but I'd like to know a bit more about it, what I would say to you is, work is an interesting one because it is scalar. It doesn't have direction, but it is something that we tend to see as negative and positive because we look at it as an energy transfer. So positive work is where energy is added into the system, where negative work is where energy is taken out of the system. Now, very much like what we're doing the whole video with the Hooke's law, we never care or we never deal with that negative. We take this always as positive. We will take work as positive because we deal with that energy in and out of the system in a different way. And when we're working with this, we'll be working with the conservation of energy. So we'll look at energy at different points. We don't really need to care about energy in, energy out. What we're caring about is that it's all balanced. So once we know position, how the energy at one position, the energy at the other position, we can balance those. So it's just an extra bit. This bit in blue, don't worry about it. It's not something that comes up, but it is important to kind of not get confused with that sign. Often students are just constantly plugging in that minus because it's in the formula. So it's really important that we understand what it is. So this is the SEC sample higher level paper question 7. We're going to work with part AI. So from part A, they tell us a bungee jumper of mass 75 kg jumps from a height of 35 meters above water. The jumper is tied to an elastic rope of natural length 12 meters and an elastic constant of 100 newtons per meter. Derive an expression for the work done when a spring of elastic constant K Newton per meter is stretched by X meters. So here we have work done by a varying force. The information that they gave us after part A, that's going to be needed for a future part, but it's not needed for now. This is a very generic formula we're going to derive with a K and an X. So the first thing we're going to do is we're going to get our formula for work from the log tables. And that is the one where we have a varying force. So it is force, the integral of force with respect to S, which is displacement. we need to think about what that force is. For us, it's Hooke's law, so F is equal to minus Ks. So just something to be aware of here. Work is a scalar, which means it does not have direction. Force is a vector, which is why we have that negative for Hooke's law. It is restorative force, which means it's coming back to where it started. So when we put Hooke's law in for our work formula, we're not going to put the minus. We're not going to put the direction. There is no need to do that. So we're just going to integrate Ks with respect to S. We're moving it from a displacement of 0 to x, so I'm going to use limits of integration here. So that allows us to get ks, add 1 to our power, divide by our power, and we're going to evaluate that between 0 and x, which gives us k x squared over 2 minus k times 0 squared over 2, which gives us work is equal to kx squared over 2, and work is measured in joules. So part 2 tells us that the motion of the bungee jumper may be modelled using the principle of conservation of energy. Using this model, calculate the distance between the water and the bungee jumper when the bungee jumper is at the lowest point of their motion. Now, what I want to point out is in part 1, we did work out a formula for work done, which was kx squared over 2 joules, where x is the displacement. Now, notice how this is measured in joules. So we're going to use this within the question. So before we go any further, let's sketch out what's happening. So we have a bungee jumper who is at a given height. So here is where they're jumping from, and this is 35 meters. So we have this jumping point here at the top. We then have a few more measurements that we want to put in. One is the natural length of the rope, which we know is 12 meters. That rope, because it's elastic, can then extend to the lowest point of motion. We're going to call this extension X because that's in line with how we worked in part 1. And then we have the water here at the bottom, and we want to find that distance between the lowest point of motion and the water, which is h. So the purpose in this question is to find that value of h. So when we think about the principal conservation of principal conservation of energy, we're going to talk about 2 of these points. The first point is going to be the jump point, and then the second point is going to be the lowest point of motion. So we know the energy at the jump point should equal the energy at that lowest point of motion. So at the jump point, there's no kinetic energy. We're only talking about potential energy. So the potential energy here is going to be given by mgh, which is our mass, which is 75, times gravity, which is 9.8, times the height. Now you can in theory do this to the lowest point of motion. It gets a little bit tricky, so let's just go to the water. We're going to take that as our lowest point. We work that out, so put that in the calculator, and we know the total energy at the start is 25,725 joules. So then at the lowest point of motion, we still have potential energy. There is no kinetic energy because it is the lowest point of motion. This bungee jumper has stopped. So we have potential energy, which again is mgh, which is 75 times gravity, 9.8, plus the height, which we don't know, which is h. Let's tidy that up. That gets us 735 h joules. But there is something else at play here at position 2. Because of the stretch, there is a potential for that elastic to pull back up, that restorative force due to Hooke's law. When we think about that, we can include the work done as part of this conservation of energy. So we're going to add work in here, which is going to be, so I'll do an equals plus k, which we know is 100, times x squared, so that's your extension, we don't know that, all over 2. Meaning here at this point we get 735h plus 50x squared. Now the issue at the moment is there's too many unknowns. We have a h and an x. this will all be measured in joules. So can we rewrite x in terms of h? So let's go back to our diagram and we can say, well, 12 plus x plus h should give me the total 35, meaning I can rewrite x as 35 minus 12, which is 23, minus h, which allows us then to only have one unknown. So 735h plus 50, 23 minus h squared. So what we know, and again, if you want to keep our units on that, it's going to be in joules. So what we know is the energy at position 1 will be equal to the energy at position 2, meaning 25725 should equal 735h plus 50 times 23 minus h squared, and we're going to expand that bracket, tidy that up, we should get a nice quadratic and solve that for h. So just giving ourselves a little bit more space to work out this quadratic. So 25725 is equal to 735h plus 50. Let's expand. 23 by 23 is 529 minus 46h plus h squared. Multiplying that out, I know the numbers are quite big, so do take care. 735h plus 50 by 529, that's 26450 minus 46h by 50, 2300h plus 50h squared. We have our quadratic. We're going to bring everything to the right hand side. So I have a 50h squared. We're adding these two pieces together first, which ends up giving us minus 1565h. Then we have 26,450 minus 25,725. When that comes over, that's 750 equals, 725. And that equals 0. So you can even like this go straight to minus b, but the numbers are quite big. Everything is divisible by 5. So that gives us 10h squared minus 313h plus 145 equals 0. So that gives us h equals minus b plus or minus square root b squared minus 4ac all over 2a. Two answers then for h. So we're going to get 0.47 and h equals 30.8 meters. Now you might think both of these are valid. However, remember we said that x was equal to 23 minus h. In order for then x not to be negative, h had to be less than or equal to 23. If it was equal to 23, we get an x equal to 0. So because of that, this answer here is not valid. And our actual answer is h equals 0.47 meters.